Hello, greeting to you all. My name is Muhammad Abdul Malik and I am from CSE Department D section and I am here to display my Tech Talk topic of data structures. The topic name is going to be Community Aware Graph Signal Processing. Modularity defines new ways of processing graph signals. Let's begin. Introduction to Graph Signal Processing. Definition: Graph signal processing, which can also be called as GSP in short form, extends traditional signal processing to data defined on irregular graph domains. Key ideas: nodes is equal to signal carriers, edges is equal to relationship. Example of graph signal: temperature reading across sensor networks, social networking interactions like shares, opinions, brain connectivity network with neural activation levels. Importance: enables filtering, denoising, prediction, and transformation of signals structured by graphs. Why GSP matters today. Content for slide. Explosion of network structure in data, social media, biology, genomics or proteomics, transportation, IoT, and 5G or 6G system. Needs: tools that extract insight from signal living on this network. GSP provides filtering, denoising, compressing, prediction. Limitation of traditional GSP: relies on Laplacian agent basis. Traditional GSP uses spectral decomposition of the graph Laplacian. Overemphasis on local structures, good for node level relationships, but weak in capturing mesoscale structures. Loss of modularity. Community structures which often define real world behavior are ignored. Computational challenge. For a very large graph, again, decomposition is expensive. Result: incomplete understanding of network data. What is modularity? The definition is: modularity measures how well a network is divided into communities or clusters. High modularity: strong communication structures, dense connection within, sparse between applications. Identifying group in social networks, detecting functional brain modules, group grouping users or items in recommendation systems. Community aware perspective. New direction. Instead of processing signals only at the node level, consider community level signals. Concept: community acro- communities act as micronodes or supernodes in the graph. Benefits: reduces dimensionality, faster computation, enhances interpretability, results meaningful at group level, preserves essential structures, properties of a graph. Why community aware GSP? Real world motivation. Social media opinions spread mostly through communities, not individuals. Brain activity often shows modular activation patterns, not random nodes. Advantages over classical GSP: captures both local and global structures, enables more accurate filtering and signal reconstruction provides scalable framework for a very large graph. Methodological framework step in community-aware GSP graph partitioning detect communities Loven, Girvan Newman, spectral clustering. The second one is going to be signal aggregative. Aggregate node level signal into community level signals. Community based transform define transform and filters at community scale. Processing stage perform tasks like denoising, compression, prediction, reconstruction. Map process signals back to original node space if needed. Community-based transform traditional Fourier basis eigenvectors of graph Laplacian. Community-aware basis derived from community partition. Key advantages: lower dimensional space, fewer components, reduces noise from individual node fluctuations, improves efficiency in real-time applications. Example: community-aware Fourier transform, which can be listed in short form as CAFT, transforms node signals into community signal space. Advantages and the challenges. Advantages are captures hierarchical structures of a graph, efficient scaling to large graphs, reduces interpretable results for decision making. The challenges are going to be community detection algorithm vary in accuracy, resolution limit problem. Some small communities may be missed. Lack of standard community-based transformation still evolving, balancing node-level details with community abstraction. The applications are going to be social networks, opinion dynamics tracking, and viral content prediction, biological data, in that brain activity, for example, MRI modular signals and protein interaction signals, sensor networks, environmental monitoring, grouping sensors regionally, recommendation systems, detecting communities of users and items, better personalized recommendations. Case study or example. Scenario: a social network with 1,000 users. Traditional GSP operates on each user activity, complex, noisy data. Community-aware GSP communities, interest groups, example gamers, movie fans, sport lovers, aggregate signals, group level behaviors, result cleaner pattern of information diffusion, faster computation, improved prediction of viral trends. Comparison with traditional GSP. Traditional GSP involves node level analysis, high computational burden, misses modular organization. Community aware GSP involves community level abstraction, reduce computation, preserve community dynamics. Case study or the brain network. Brain graph for MRI is equal to average of 90 region. Signals is equal to neural activity per region. Community aware GSP detects functional modules like motor, visuals, memory, improves interpretation of modular activities. Applications are neurological disorder analysis. Visual workflow. Input is equal to graph plus node signals. community detection, clustering, signal aggregation, node community, processing, Fourier-like transforms, filters, denoising, output, community signal or reconstructed signals. Methodological framework, graph partition, to detect partition, signal aggregation to computational community level signals, define transforms and filters at community scale, perform signal processing, for example denoising, filtering, or compression, reconstruction, map back to node space optional. Theoretical foundation. Spectral graph theory used Laplacian eigenvectors for frequency, community detection, Leuven-Gervin-Newman, spectral clustering, signal aggregation theory, projection of signals from node space to community subspace, hybrid theory, combined node plus community signal for richer models. The conclusion and future directions are going to be, the conclusion is community aware GSP integrates into work science community detection with signals processing, provides a new paradigm for analyzing graph structure data, future work, adaptive community detection to dynamically updated communities as graph evolves, hybrid modules combined to node level plus community level GSP, broad applications to IoT networks, neuroscience, recommendation engine, cybersecurity. Takeaway: community aware GSP make processing scalable, interpretable, and closer to real world structures. Thank you.